We are currently looking at two lights approximately 15 billion light years away from our world, two separate celestial bodies. The reason they appear so bright from such a distance is that these objects are very mysterious bodies called quasars. But that's not our topic. These objects were first observed through a telescope in England in 1979, and scientists naturally gave them separate names. They called one 957 and the other 561. Then they continued their investigation. Something was strange. These objects resembled each other a little too much, in every way. All the studies revealed strange similarities. They seemed to be the same. More than just similar. These two objects were actually the same. It had to be so. Perhaps it was meaningless, but that was the case. It was the same for astronomers too. It was like seeing a mirage in the desert, but one of them would eventually solve the problem. Yes, they weren't wrong. Because what they saw as two separate objects, what they named two separate objects, was actually a single object. And a man had already predicted and theorized this 100 years ago. The world's first famous scientist, a man who was treated like a superstar while he was alive, a phenomenon who taught many people what it means to think outside the box. Albert Einstein, the man who explained to us at the beginning of the 20th century that all of humanity had misinterpreted the universe for thousands of years, that even geniuses like Isaac Newton could be wrong. In the video, What is Time?, we introduced Einstein's universe and laid the groundwork. Now, I want to take a deeper look at the universe through Einstein's eyes, and of course, at the theory of general relativity that changed everything. I think the word that best describes Einstein's universe is space-time. We call it space-time. Space, as we know it, is the three-dimensional place or space. So we live in a universe with length, width, and height. You may remember from that video that time was thought to exist outside of this. Einstein's groundbreaking discovery was that time is not independent of this space. In the universe, time and space are so intertwined, so inseparable, that we can think of them as a single fabric, like an entity upon which all objects in the universe move. We call this entity space-time. Isaac Newton described the universe as a stage, like a box in which everything happens. And in this universe, everything was in a vacuum. All celestial bodies, including our world, influenced each other in this vacuum as if connected by a string. All stars, galaxies, but that was it. Einstein's universe, however, the universe as Einstein defined it, is completely different. As I mentioned, everything moves within an entity, not in a void. Space is not empty. All celestial bodies move within this formation, which you can think of as a dense liquid. And depending on their size, all planets, all stars, all galaxies bend, stretch, and expand at the space-time they inhabit. Now let's return to the single quasar we saw as two. It was the interaction of matter within the space-time that caused this interesting situation, and the only explanation for seeing a single object as two could be this bending of space-time. The light emanating from this massive quasar encounters another massive galaxy or group of galaxies between it and us, and this light is bent due to the warping of space-time by these galaxies. These galaxies, which could consist of billions of stars, warp space-time so much that when we look at them, we see the quasar behind them as a double. There's a name for this phenomenon. We call it the gravitational lensing effect, the bending of light. But this discovery is more than just an explanation for why we see double, an optical illusion. It is actually proof of everything Einstein calculated and tried to explain. Proof of the general theory of relativity. Because Newton's biggest problem was that although he could calculate gravity, he could never explain how it worked. He basically said, "This is as far as I can go." He made incredible calculations, but he got stuck here. He said, "You solve it now." When Einstein did it, it was like saying, "Open up, I'll take care of it." And he really did take care of it, with the theory of general relativity. The theory he described was actually quite simple. What we call space, what we think of as emptiness, is not actually emptiness. It is space. It is something that physically exists. And this phenomenon we call space-time is explained in its simplest and most general form as shown in this video. Gravity is actually the movement of smaller objects along the curvature created by massive celestial bodies bending space-time, as seen in this video. So what did he say? Einstein. You remember. Newton. I'm so sorry. He was both sad and very happy again, because Einstein had discovered that there was no such thing as gravity. Yes, there was no such thing as gravity. Objects did not attract each other, they only moved within the boundaries of the curvature they created in space-time. He said that you, me, the sun, galaxies, everything with mass and energy creates this curvature. The quasars mentioned earlier are actually a newly discovered piece of evidence, just one of dozens of pieces of evidence found. Einstein decided to test his general theory of relativity during a solar eclipse with the help of astronomer Sir Arthur Eddington. In this theory, Einstein had also calculated exactly how much this curvature of spacetime would bend light, at exactly 1.75 arcseconds. This measurement, used in astronomy, simply shows the angle at which you view an object in space. When you divide a degree by 60, you get arc minutes, and when you divide that by 60, you get arcseconds. Einstein made such a precise calculation. And his claim was about to be tested for the first time. Sir Arthur Eddington, during the solar eclipse, first measured the actual position of the Hyades star cluster, which would be behind the sun, to measure how its light would bend. Then he assigned two teams, one in the Gulf of Guinea in Africa and another in Brazil, to take measurements again during the solar eclipse, as there was a risk of cloudy weather. These teams measured the light coming from the Hyades star cluster, which was behind the sun during the total solar eclipse. Incidentally, the reason they chose a solar eclipse was that normally, due to the sun, it was impossible to obtain a very clear image of these star clusters. Only when the sun was present and it was dark enough could such a precise measurement be made. After returning to England, Eddington collected the data and found that the light was bent exactly as Einstein's theory predicted, with zero deviation. The next morning, after publishing his findings, Albert Einstein became a household name around the world in a single day, etching his name into history forever. Now let's return to a topic we left unfinished in the previous video, the deviation in Mercury's orbit. In that video, I deliberately avoided giving a full explanation on the subject, because without discussing the general principle, we couldn't understand this deviation which had remained unexplained for centuries. Newton and Kepler before him had tried to explain the orbits of the planets and had made incredibly precise calculations for their time, and everything fit the book, except for Mercury. In the elliptical orbits of the planets, there are points closest and furthest from the Sun, known as perihelion and aphelion. All planets experience some deviation over time. We call this precession. If all planets experience precession or deviation, why was Mercury's deviation such a problem? Because when calculated using Newton's theory, there was a difference, albeit a very small one. While all other planets fit the calculations perfectly, Mercury just wouldn't match up. We mentioned it. It was said that there might be another planet, but there wasn't. Then, for centuries, all scientists thought, well, that's how it is now. We calculated it, but there's a slight difference. There's something we don't understand. They said there was some kind of gravitational magic. They said we shouldn't mess with it too much. But Einstein did mess with it. Actually, he didn't start directly with Mercury, but when he proposed the theory of general relativity and explained spacetime, everything fell into place. When the deviation in Mercury's orbit was recalculated using Einstein's formulas, it matched perfectly with zero deviation and zero error. Because a planet experiences this deviation, this movement, more intensely at its perihelion, the point closest to the sun, due to the curvature or bend in spacetime caused by a massive celestial body like the sun. No matter where you look, no matter which galaxy or celestial body you calculate, Einstein's general theory of relativity gives the exact answer. It explained all movements in the universe. But finally, I want to tell you about a very strange event that happened very recently, an event that if Einstein had been alive when it was captured on camera, would have filled his eyes with tears. Gravitational waves. Now, if we consider that space is not empty, and every event that occurs in the fabric of space-time affects this fabric, for example, the collision or merger of two black holes would result in a massive explosion, and an event of this magnitude would have to affect this fabric on a very large scale, right? Think of a drop of water falling into water, or throwing a huge rock into water. You will see waves spreading across the water with this effect. Einstein predicted these waves but thought they would be very difficult to observe. He wasn't wrong given the technology at the time. But technology advanced. It advanced significantly. And you know what happened? In 2016, an observatory called LIGO, whose primary purpose was to detect these gravitational waves, made history. the scientists who brought this project to life detected for the first time the gravitational waves produced by the merger of two black holes, an event that released an extraordinary amount of energy. And when I say extraordinary, I mean something like this. It could be comparable to the total energy output of all the stars in the observable universe. It was precisely because of this immense energy that the resulting gravitational waves were detected. The existence of these waves had already been established theoretically in 1974 by certain scientists, but for the first time, they were directly detected using instruments, sensors, and lasers. For this discovery, the LIGO team was awarded the Nobel Prize in Physics in 2017. The people who detected, with actual measurements, a phenomenon that had been proposed purely theoretically by one man 100 years ago received the Nobel Prize. I think this is just one of thousands of reasons that help us understand what kind of person he was, what kind of genius. When people hear or read all this, they might think, Einstein finished physics. He explained everything. We can all go home. But in reality, everything was just beginning. An entirely different world was waiting for us. The fourth dimension that Einstein introduced would not be enough. Fifth dimensions, 10th dimensions, even thousands or perhaps countless dimensions. Cats that can be both dead and alive. Particles that exist in different places at the same time yet remain in telepathic communication with one another. Erwin Schrödinger, Niels Bohr, Werner Heisenberg, Max Planck, Max Born were waiting for us. The quantum world was waiting for us. Until we meet again, take very good care of yourselves. And as always, I'm grateful you exist. With love,